Welcome to this model. In this presentation, we'll speak about some of the micro semiconductor devices like a gun diode and impact diode. Micro solid state devices can be classified into two major types: avalanche transit time devices and transferred electron devices. In avalanche transit time devices, when a PN junction diode is reverse biased, no current flows. But when a reverse voltage exceeds the junction breakdown and current flows with only slight increase in voltage, and this breakdown is caused by the avalanche multiplication of electrons and holes in the space charge region of the junction. So the PN junction exhibits negative resistance characteristics in the avalanche breakdown conditions, and this negative resistance region is used to generate microwave power and to amplify microwave signals. Such devices are called avalanche transit time devices, and examples are impact diodes, barrier diodes, and trapper diodes. And the second category is transferred electron devices. So in electronic devices at micro frequencies, negative conductance effect was discovered by Gunn as bulk effect. This bulk effect property of a material may be obtained by reduction of electron drift velocity with increase in electric field above a threshold value. The electrons shift from high mobility to low mobility state under the influence of the strong electric field. Such phenomena is called transferred electron mechanism, and device that exhibit this feature is called transferred electron devices. One example of transferred electron devices is gun diode. So, a gun diode is a passive semiconductor device with two terminals, which composes of only n-doped semiconductor material, unlike other diodes which consist of p-n junction. Gun diodes are also known as transferred electron devices. Although it is referred as a diode, the device doesn't possess any p-n junction. So instead, the device uses the effect known as the Gunn effect, named after the discoverer J.B. Gunn, and the Gunn diode is normally used for generating microwave RF signals. Transferred electron devices are one of the most popular microwave devices used as oscillators and power amplifiers. These gun diodes can be used as bulk devices without junction, and they are fabricated from gallium arsenide and indium phosphide. And this gun diode operates with the hot electrons having more thermal energy. TDs are tunable over a wide frequency range with low noise characteristics. So this figure shows the structure and symbol of the gun diode. Even though there is no PN junction but called a diode with respect to positive and negative terminals of DC bias applied, as the DC bias is increased, the current through it is also increases gradually. And when the DC voltage increases sufficiently to produce electric field of 3.3 kilovolt per meter second, the current decreases with increase in voltage. This results in negative resistance effect. So this negative resistance property is used to produce oscillations at microwave frequencies. So gun diodes are fabricated from a single piece of n-type semiconductor. The most common materials are gallium arsenide, indium phosphide, and however other materials may also include GE, CDTE, INAS, INASB, and ZNSC, and others have been used. The device is simply an n-type bar with the n plus contacts. So on applying DC voltage across the terminals of the gun diode, an electric field will be developed across its layers, and most of which appears across the central active region. At initial stages, the conduction increases due to the movement of the electrons from the valency band into the lower valley of the conduction band. So the associated VI characteristics is shown in this figure. However, after reaching a certain threshold value, the conduction current through gun diode decreases, and by the curve which is shown by the curve in the blue color region. And this is because at higher voltages, the electrons in the lower value of the conduction band moves into a higher value where their mobility decreases due to an increase in their effective mass. So the reduction in mobility decreases the conductivity, which leads to decrease in current flowing through the diode. So as a result, the diode is said to exhibit a negative resistance region in the VI characteristics, and this effect is called as transferred electron effect, and thus gun diodes are also called as transferred electron devices. And before going into the advantages, the equivalent circuit of a gun diode can be represented with resistance, inductance, and parasitic inductance and capacitance. Where RS is the total resistance of leads, ohmic contacts, bulk resistance of the diode, and LP is the package inductance, and CP is the package capacitance, and RJ is the diode resistance, and CJ is the diode capacitance. Gun diodes can be operated in different modes, different four basic modes: gun oscillator mode, state amplification mode, LSA oscillation mode, bias circuit oscillation mode. So in gun oscillator mode, operating frequency multiplied by length will be equal to 10 power 7 centimeter per second, and the doping multiplied by length should be greater than 10 power 12 centimeter square. In this mode, the device is unstable. Higher oscillation frequency can be obtained when the device is operated with a high Q cavity resonator. In stable amplification mode, the operating frequency multiplied by length should be equal to 10 power 7 centimeter per second, and the doping multiplied by length should be equal to 10 power 11 to 10 power 12 per centimeter square. In LSA oscillation mode, that is limited space charge accumulation mode, the operating frequency multiplied by length should be greater than 2 into 10 power 7 centimeter per second, and LSA mode is the simplest mode of operation. In this mode, the gun diode is placed in a resonator, which is tuned to an oscillation frequency of F0. So in this mode, the device can be biased to several times the threshold voltage. As the input RF voltage increases above the threshold voltage, the device remains in the negative resistance region, and the oscillating frequency is determined by the external components only, but not by the transit carrier time. The output is obtained in LSA mode is much greater, and the output power of the oscillator in LSA mode is given as P is equal to eta into I naught into V naught, where eta is the conversion parameter of material, and P can also be written as eta into M ETHL into N naught EV naught into E, where I naught is the operating current and V naught is the operating voltage, and M is the multiplication factor, and ETH is the threshold electric field, L is the device length, and N naught is the donor concentration, and E is the charge of electron, and V naught is the average carrier velocity, and A is the device area. And there are some limitations in LSA mode, which are LSA mode is very sensitive load, and LSA mode is sensitive to operating temperature, and variation in doping concentration affects the frequency stability. And the main advantages of gun diodes are its high bandwidth, high reliability, and low manufacturing cost, and its fair noise temperature, and relatively low noise or low operating voltages. And the major disadvantages of gun diodes are its low efficiency below 10 gigahertz, and poor stability, that is the frequency varies with the bias and temperature, and FM noise high for some application, and small tuning range. And gun diodes can be used as low and medium power oscillators in microwave receivers, in parametric amplifiers as pump sources, and in radars, and it can also be used as broadband micro amplifiers. And next, let us have a look into impact diode. Impact diode exhibits negative resistance, which can be obtained by junction diode of any doping profile. Impact is derived from the word impact avalanche and transit time. Impact diode consists of high doping avalanche region and a drift region. And three typical silicon impact diodes are one-sided abrupt PN junction, linearly graded PN junction, and pin diode. So impact diode is a very high power semiconductor device that is utilized for micro applications. It is basically used as an amplifier and oscillators at micro frequencies. The operating range of the impact diode lies in the range of 3 to 100 gigahertz. Basically, it possesses negative resistance characteristics, thus act as an oscillator to generate signals at microwave frequencies. It is a reverse bias diode, and avalanche condition is the basis of its operation. An impact avalanche and transit time diode has a physical structure similar to the pin diode, but is operated with a relatively high voltage 70 to 100 volt to produce a reverse biased avalanche breakdown current. This diagram shows the structure of the impact diode. It consists of an N layer and I layer sandwiched between P plus and N plus layer. It consists of, as I said earlier, it consists of four regions, namely P plus, N, I, and N plus regions. Generally, materials like gallium arsenide, silicon, germanium, and indium phosphide are used for its construction. However, gallium arsenide is preferred because of its low noise behavior. An action that causes an abrupt increase in the junction current and reverse bias condition of a PN junction diode, leading to junction breakdown, is known as the Avalanche breakdown. We know that in reverse bias condition, the width of the depletion region becomes extremely thick, due to which only minority carriers drift across the junction. In the presence of high electric field and the mobile charge carriers move with a greater velocity. So during this movement, the high velocity carriers collide with the other atoms in the crystal and generates electron hole pairs. And this causes the multiplication of charge carriers inside the crystal structure. Thus, moving charges generate high current inside the device. And this is known as the avalanche condition or impact ionization, and is utilized in impact diodes. Initially, when AC voltage is 0, then due to applied low DC voltage, a very small amount of current flows through the diode. And this current is generally known as the pre-breakdown current. But as the applied voltage increases, and then the electric field inside the diode increases. And as we have already discussed that with an increase in electric field, there will be an increase in number of generated electron hole pairs due to impact ionization. And the increase in superimposed AC field and DC potential causes the electrons in the P plus region to get injected into the I region in order to drift towards the N plus region. And this is so because with the increase in the applied field, the electrons will move towards the anode and holes towards the cathode. And this diagram shows the characteristics of the impact diode. This graph has that maximum resistance is offered at theta is equal to pi. And above pi Z, and the resistance decreases rapidly. And the operating frequency around the pi transit angle is F is equal to 1 by 2 tau, and F is equal to Vd by 2L, where tau is the transit time and Vd is the drift velocity and L is the drift length. And the maximum output power is given by Pm is equal to Vm into Im, that is Pm can be written as Em squared epsilon s Vd into A, where Em is the maximum electric field and Vd is the drift velocity and A is the cross section area and epsilon s is the semiconductor permittivity. So the efficiency of the impact diode can be written as PAC by PDC, which can be written as VA into IA divided by VD into ID. And the main advantages of impact diode are it provides high operating range and it shows compactness in size and they are economical, and it provides reliable operation at high temperature. And the major disadvantages are the rate of generation of electron hole pair in the avalanche region causes the generation of high noise, thus makes the system noisy. It offers a low tuning range and it offers high sensitivity to different operating conditions. And the applications, and the impact diodes find applications in micro oscillators, parametric amplifiers and micro generators. Along with this, other uses involves presence in intruder alarm systems, telecommunication transmitters and receiver. Thank you.